It looks like it's going to be a cold one today. An Arctic cold front moved into our area around 3 this morning and has already dropped 3 to 4 inches in some parts of the city. The air mass associated with this front is stable, and with all the moisture that's being pushed up from the Gulf, we're in for snow the rest of the day and possibly tomorrow.
Every day, all over the world, people are dealing with the effects of the weather. In the previous section, we saw how the forces of air density, Coriolis, temperature, and moisture worked independently of each other. In this section, you'll see how they interact to produce the weather phenomena we see every day. The type of weather we experience is, in part, related to whether or not air rises or falls in relation to the surrounding air. The term used to measure how much relative resistance an air mass has to this vertical movement is called stability. A stable air mass, for example, resists vertical motion. This inhibits large cloud formation, heavy precipitation, and severe weather. An unstable air mass, on the other hand, has the potential for significant cloud development, turbulence, and hazardous weather. The weather in the tropics is a good example of unstable air. With its warm temperatures and high humidity, daily thunderstorms are commonplace. Air mass stability plays a large role in the development of weather. We can best see this role in the development of clouds. There are two basic types of clouds, cumulus and stratus. Cumulus clouds are formed by rising currents of air, which gives them a piled up or bunched appearance. They warn of unstable air, turbulence, and showery precipitation. Visibility outside the precipitation is usually good. In air masses with a high amount of stability, stratus clouds may form. Resisting vertical movement, these clouds form in smooth layers and often extend over large distances. Since the air is stable, flight near stratus clouds is normally smooth. Precipitation from these clouds can be continuous and last for several hours or even days at a time. The visibility associated with stratus clouds is usually poor. In addition, clouds can further be grouped into high clouds, middle clouds, low clouds, and clouds with extensive vertical development. Cirrostratus, cirrocumulus, and cirrus clouds are examples of high clouds. They are composed almost entirely of ice crystals and seldom pose hazards to pilots. Most names of middle clouds contain the prefix alto, such as altostratus or altocumulus. These clouds are composed of water, ice crystals, or supercooled water, which is water that has been cooled below its freezing point but is still in a liquid state. They can contain moderate turbulence and potentially severe icing. A cloud with a name containing the prefix nimbo or the suffix nimbus contains a large quantity of moisture. A nimbostratus cloud, for example, can produce widespread areas of snow or rain. While classified as a middle cloud, the nimbostratus cloud can merge into the clouds formed at low altitudes. A cloud which can be very deceptive to pilots is the lenticular cloud. This lens-shaped cloud may form over mountain crests during high wind conditions. Even though it looks smooth and serene, it is, in reality, a good indication of heavy turbulence and should be avoided. The low clouds form near the surface and extend to around 6,500 feet. Clouds within this group include the stratus, stratocumulus, and fair weather cumulus clouds. The thunderstorm, or cumulonimbus cloud, is an example of a cloud with extensive vertical development. This type of cloud can have its base as low as 1,000 feet and extend up to the heights associated with high clouds. Flight near a thunderstorm can be extremely dangerous. These hazards will be discussed in the next section. So far, we have talked about the stability of an air mass and the types of clouds which can form if the air mass is stable or unstable. But how and where do these air masses begin, and what happens to them as they move? As we discussed earlier, the global circulation patterns form high and low pressure areas. The The high-pressure areas, located at the poles and in the tropical areas, act as source regions for air masses. If an air mass forms over water, it is further classified as maritime. This type of air mass will usually contain more moisture than a continental air mass, which forms over the land. As an air mass leaves its source region, it is modified. The amount of modification depends on the speed of the air mass, the nature of the region over which it is traveling, and the difference in temperature between the air mass and the region. As an air mass moves, it comes in contact with other air masses of different properties. Since air masses with different temperatures and pressures do not mix very well, their boundary forms a front. As you fly across a front, you may experience discontinuities, which are rapid changes in atmospheric conditions. These include temperature, wind, and pressure. Temperature is probably the most easily noticed change, but the two which should concern you more are wind and pressure. An undetected change in the wind could cause you to drift off course inadvertently. When flying through a front, you should expect a wind shift and adjust your navigation accordingly. Since there is usually a pressure change when you cross a front, you should reset your altimeter to the correct setting to avoid being higher or lower than the indicated altitude. Fronts are defined by the type of air mass that is in the overtaking position. In other words, if a colder air mass is overtaking a warmer one, then the resulting front is called a cold front. This definition is relative, though, because a cold front can be any temperature, as long as it is cooler than the air mass it is overtaking. As a cold front moves, it replaces warmer air at the surface. Since colder air is denser, it pushes the warmer air aloft. If this warmer air is relatively dry and stable, stratiform clouds form in the vicinity of the advancing cold front. If the warmer air is relatively moist and unstable, cumuliform clouds may form along the front. A rapidly moving cold front can create thunderstorms many miles ahead of the frontal boundary. A line of these thunderstorms parallel to the front is called a squall line and can contain violent weather. The thunderstorms in a squall line can grow to 65,000 feet and can be especially violent. These storms often produce heavy rain, large hail, and even tornadoes. In contrast to a fast-moving front, the slope of a slow-moving cold front is not as steep and the lifting action is not as great. Therefore, the weather is less severe. When a warmer air mass overtakes a colder one, a warm front exists. Because of the difference in relative densities, the warm air will slowly slide over the colder air. This can result in very little vertical air movement. If enough moisture is present and the colder air mass is relatively stable, stratiform clouds usually form. These clouds may extend for many miles ahead of the front. However, there may be some cumulus clouds present in the form of embedded thunderstorms if unstable air is present. The weather associated with a warm front usually includes low ceilings, fog, and a subsequent reduction in visibility. When two air masses of relatively equal strength collide, a stationary front may form. Here, there is very little movement. The weather associated with this front can vary depending upon the temperature, moisture content, and stability of the air masses. It is usually a mixture of that found with both warm and cold fronts. One of the most complicated frontal systems is the occluded front. In this case, a fast-moving cold front is overtaking a slower-moving warm front. There are two types of occluded fronts. The one shown here is a warm front occlusion because the air ahead of the warm front is colder than the overtaking cool air mass. Of the two types of occlusions, this one produces the more severe weather. The other type is a cold front occlusion. Here, the cold air is replacing cool air at the surface. This type of occlusion generally doesn't produce weather as poor as a warm front occlusion. However, like the warm front occlusion, the weather associated with it is hard to predict and can produce a wide variety of weather considered dangerous to most general aviation aircraft. With weather patterns constantly changing, it is important to understand the factors behind their development and to get a good pre-flight weather briefing before flying. In the next section, we'll take a look at how these weather systems can be hazardous to flying and what you can do to predict these conditions and avoid them.